So with that, please join me in welcoming the inventor of Erlang, Joe Armstrong.
Are we ready? Okay, thank you. Well, thank you, Garrett, for that very complimentary introduction. When I said I was going to come and give this keynote speech at Lambda Jam, and then it just turned out that there was an Erlang user group meeting just while I happened to be here. So I thought, oh, that's great. I'll ask if I can go to it. And so just by coincidence, the two fell in the same week, which is very, very fortunate, actually.
Amazing point.
Yeah. And so that actually got, and then Garrett said, well, don't bother with any sort of great preparation for talks. So I thought, wonder what I'd talk about, and kind of delayed a bit. And then I saw the list of people who are coming to this, and I thought, well, some of them knew Erlang, because there was a question. It's quite helpful when you're giving a talk to know what people know, so you can choose the right sort of talk. And I saw that some people knew Erlang, and other people didn't know it at all. And you're kind of technical people. So I've taken this talk, which I gave, actually, this was given there's an Erlang company in Stockholm called Klarna, and they had a kick-off meeting for a new project. They have 200 Erlang programmers, and they've grown to 800 people in 5 years. And they're more, I think the first company that's pure Erlang is worth $1 billion. And they had a kick-off meeting for a new bit of technology that they were starting to program, and I was invited to give a talk there. So that was an audience of people who are Erlang programmers and sort of project managers. I mean, they don't know anything about programming or anything like that, and management types and sort of generally technically interested. I thought I would make a talk for them that was a bit of the history of Erlang and didn't assume so much knowledge about it. So I'm just going to do that again. And then I'm going to have a quick beer and a bite to eat. And then I'm going to talk about a problem that's interested me for many years. It's called the Sherlock problem. And it's I made some attempt to do it in the last chapter of the second edition of my Erlang book, and I've had some ideas since. I realized as soon as I published the book and things, there's a much better way of doing it, so I can't retract the chapter, but it's kind of an interesting problem, and I've been thinking about it for many years, so I thought I would just talk to you a little bit about that. So this is, there we go. So this is how I got my, when I started Erlang, I didn't have any grey hairs, and the other people who also developed, I mean, Mike Williams, and you met Mike and Robert, they didn't have any grey hairs either. So one thing that happens if you develop programming language is you get grey hairs from doing it, and you get one grey hair for every mistake you've made. So that's why I've got quite a few grey hairs. Weren't any, and if I'd been in Silicon Valley, I'd be a squillionaire. I'm going to use a history chart to show what sort of happened, what you have to do to develop a programming language. If you're a sort of academic or something, you think that the way of developing a programming language, you develop a programming language, it takes you 3 or 4 years, because that's the time it takes you to get your PhD, and you publish your PhD, and then the whole world will use it. It doesn't sort of work like that, actually. You've got to do quite a few other things. So this is a sort of timescale diagram that shows what was happening, the number of users we had as a function of time, and the number of developers. I mean, this is the number of people who are developing the language, and this is the users, and what they were using it for. And this is the techniques we were using to implement it with. And then there was a kind of marketing thing that you had to explain to people what it was. And it was kind of trendy to talk about declarative programming, or like it's trendy to talk about functional programming languages. So even though you're not doing functional programming, you're programming PHP, you can say, well, we're programming a functional style now because it's a trendy marketing term, and nobody really knows what it means anyway. So what we're actually doing is changing with time. And then at the same time, there was this kind of secrecy and wars, and we had great wars with the C++ people, and there was a whole thing about secretness and openness, because when we started, this was done inside Ericsson, and Ericsson there was no, I mean, in 85, there was no such thing. The word open source didn't exist. Nobody knew what open source was. So and everything you did was secret, and then it all changed. So it's kind of followed through this time period until it gets to this point in time, and then something interesting happens, and we'll see what that interesting. There's a reason why it stops there, which I will reveal later. So if we go back to 1985, is anybody born in 1985? Oh, right. And anybody not born in 1985? Oh, goodness, right. So this is what people did, before you were born and before there was an internet. We sat around inventing programming languages, and this is actually what we wanted to program. This was. I worked for Ericsson at the time. I still do. Doesn't mean to say I've worked for Ericsson for all that time. I had 8 years of not working for Ericsson. Now I work for them again, and this was what we made at the time. We made telephone exchange, what we still make telephone exchanges. And in those days we made telephone exchanges that used copper wires between telephones, and there were no mobile phones and no radio communications or anything like that. And they were programmed in a language called Plex. And wanted to try and program this stuff. So around about 1985, I got a job at the computer science lab, and this lab was just newly formed. And one of the things we wanted to do was to find a programming language that was better than Plex. Because Plex wasn't a really it's a sort of horrible language. Well, I mean, it was very good for its time, but it was like real-time BASIC with parallel processes. So if you imagine BASIC programs, the basic programs had to be very, 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 very small, but you could have millions of them executing in parallel. Well, not millions, maybe hundreds of thousands. And they each had their own set of protected memory and their own set of registers, and they all ran in parallel. And they ran on this product called an AXD, and they were actually pretty difficult to program. The first one came out in about 1978 or something like that, and they were the first things with stored program control. And in fact, from that day onwards, Ericsson and the telecoms company have been building planetary-wide communicating networks of systems. So, I mean, years before the internet was invented, AT&T and Ericsson had planetary-wide networks running computer-controlled switches. So it could be said that we predated the internet by several years, and there's an awful lot of experience there that is still in the telecoms industry. It hasn't really moved into the internet industry. Things like reliability we're very keen on, and it doesn't seem to have got into the internet industry yet. So the mantra when we were building these things was 4 minutes of downtime per year, because we used to pay penalty clauses if the stuff was out of service for more than 4 minutes, and you got fined, $10,000 fine if it was 4 minutes and 1 second. And so this was just unthinkable that we would be more than 4 minutes, and that's about 5 nines, something like that, 5 to 6 nines of reliability. So we had to hit those figures in the mid-70s and then onwards. So it's kind of really surprising to me that the computer industry can't do better than that with machines that are maybe 100 million times more powerful than the machines these were programmed on. Right. So here's I just looking. I have this box at home called the history box, which the only reason it still exists, I mean, my wife was always going, look, can't you throw all those stupid bits of paper away? And half, at any one garbage collection, half of them would get thrown away. And I said, well, can I keep a few of them? Somebody might want to look. I might want to look at them in the future. So I've got this one little box of all this stuff, and now I won't let her. It's down to one box, and I won't let her throw anything else away. And quite a lot of it here. I've scanned some of the things in the history box, so this is the first. This is the first version of Erlang I can actually find. There were versions that were earlier, because even at that time, you see the comment at the top, version 1.03 was lost in the mists of time. But this was version. This must be version 1. Yeah, this is version 1.06, which is on the 12th of December in 1986, and version 1.03 was lost in the mist of time. Version 1.04 had modules and peeping. I don't know what peeping is, actually. I can't remember. And version 1.05, the mean version, I don't know why it says mean, fails in top loop to conserve space. And version 1.26 added process constants, added command, start procedure, p constant, added table-driven number analyzer, and things like that. And this was, if you look at this, you can see this is, it's called makesystem.pl. It was a Prolog program, okay? So I was programming in Prolog. And the failure model, does anybody know Prolog? Right, so you know what happens when a Prolog program goes wrong? It says no. Right, now no is not a very good error. Yeah, you're right. I mean, core dump is much more informative than no. Thank you. So one thing I wanted to do with Prolog was give it some sort of better stuff should happen when it fails. And the other problem about Prolog, you could only do one thing. You could only have one process. So I thought Prolog was really great. And I made an algebra to describe telephony in Prolog. But the only trouble was you could only describe one process. And if they didn't do what you'd expected them to do and you got failure, it didn't work. Right. So then I'd read Tony Hoare's Calculus of Sequential Communicating Processes, and I thought, I really like something like CSP, with messages coming in parallel processes, and then Prolog doing the logic. So I was playing with Prolog, and it's really easy in Prolog to write a meta-interpreter for another language. So I wrote a meta-interpreter for processes in Erlang, and that was this program. And that sort of trundled along quite well, and it sort of worked, and people became interested in it. And then in about this time here, where are we up to? 1986, Erlang, who worked for Ericsson Business Networks, was interested in building a telephone exchange, and she got a new architecture, and she wanted to prototype this, and didn't want to do it in Plex, and that was really the only alternative. They wanted a better language, a better way of doing this. And we got into contact with her and said, well, we'd like to work together to do this. And at the time, we had this thing. This is an Ericsson MD110, which is controlled by a computer. And a guy in the lab called Per Hedeland connected this to a VAX 11750. So one of these cables here went out, and we could control it with a VAX. And I think if it hadn't been for that, there wouldn't have been any Erlang, there wouldn't have been any of this development, because really the test of any theory was basically, can we program this thing? If we can program it, the theory works. If we can't program it, it doesn't. It was very pragmatic. And so we started working with Kerstin, and she had this way of modeling how she thought, how she wanted to. She didn't know how to program, didn't know how to program, but she was a sort of, what do you call them, a sort of systems person. She knew all the logic, the business logic of telephony. And she programmed like this, right? So she used something that she called fishbone diagrams. So this is the first version of Erlang, right? As Kerstin saw it. Okay, so this describes a sort of branching logic. You come in at the head and you go out on one of these things. So she drew diagrams that looked like this. So this is in my history file, and it's a fishbone diagram. And it actually describes telephony. And what you notice, it's not a graph, it's a tree, and it's just describing state transitions. So for example, in a new call, you can move to a connected state, or this N and F. N is go on hook, H is hook flash. There was a thing on the telephone with a hash on it, and you pressed it, that was hook flash, and if you pressed hook flash, you went to that state. These are states. And they're actually, you remember the talk you gave this morning? These are nested state machines. Exactly the same, okay? Now, I started programming this model, and I noticed that something funny happened. Actually, let's blow up one. I'll show two more slides before that. When you blow that thing up, there's a little bit of it, and it says, you're waiting for something. You get an on-hook or an off-hook. Sorry, you get an on-hook, you terminate the call and you exit. You get a hook flash, you hold the call and you start a new call, and then you're either connected and this happens. And that looks like this, okay, in this dialect. And actually it says, because it was a parallel process, you see, we're doing several of these calls at the same time. What we're saying is, in this state, we're waiting for this message that's got this. So that began to look like that, and that's in Prolog. And that is beginning to look like Erlang. That is a receive statement in Erlang, actually. It became a receive statement in Erlang. And I started programming like this, and we built we used that for about a year, and I started programming in it, and until I started programming telephony, and then I got to a state when I was programming something called pendling, or in Swedish, no, what's that in English, I don't know, call transfer. Somebody calls me, I press the hash button, and I get a dial tone. I dial a second person, maybe you know, you've called me. I get a hash tone, I dial a second number, I dial you, you pick up, and now I'm talking to you. And then what I can do is, the spec said, if I press hook, there's hook flash 1, the hash 1, I'm talking to you and you're parked, hook flash 2, so hook 1, hook 2 goes between the two people, and hook 3 puts everybody into conference. That's what the spec said. We had to program that. And I'm programming it, and I thought, well, hang on, wait a minute, this logic says, what happens if you do hook, but you don't type 1, 2, or 3? The logic says you're supposed to type hook 1, 2. What happens if you put the hook down, put the phone down, and walk away? The spec doesn't tell me what to do. What do I program? And so I went and asked Bernd Eriksson. He became the technical director of Ericsson. And he said, well, you ring the phone, it goes ring, ring, you lift the phone up again, and then you're in the same point in this state machine that you were before, so you can do hook 1, hook 2, hook 3. And I said, but that's not in the spec. And he just shrugged his shoulders and said, everybody knows. And I thought, this is crazy. We are building products with specifications and things. The specification doesn't say what's supposed to happen. And then when you get to this point in the code where you don't know what's going to happen, everybody knows who programs it. And I thought, that's crazy, because I didn't know. And I thought everybody could interpret that differently, and they could make an ad hoc decision. So I thought to myself, well, the only sensible thing to do is crash. We just crash this call because we don't know what to do. And then I thought, I was thinking of file. I had in my mind a file system. In a file system, if a program opens a file and does something and then crashes, the operating system closes the file for you. It's not still open, and then you can use it again later. So I thought to myself, well, a call is like a file. So what happens if you do this hook flash on hook? You crash the program, somebody else will watch, the operating system will watch, and it will close the call, just like closing a file. And it will just put everything to rights. And that was the origin of this thing that now I call let it crash. But what you do is you say you do not program the abnormal things, and you do not make any decisions about how to program the stuff that's outside your specification. What you do is you crash your program, you let somebody else observe it, and put back these invariants. And I thought that's the only sensible way to program, because this set of extra things that are not in the spec is enormous. And that enormous set of things is what people call defensive programming. And it's very big. It's all these states in your finite state machine that shouldn't occur. Or if they do occur, you don't know what to do. So you can't sort of write them all. The pattern's enormous. This state space is much bigger than the state space of the problem. Moreover, nobody knows what to do. Right. So what you could do is give the default behavior, crash, and let the invariants put everything back together again. And if one particular path through your code gives you some unexpected behavior that's wrong, then you can put in the patterns that describe that behavior. And that was the original philosophy of all this kind of crashing stuff. Right, so we move on a little bit. Now we can do, we're still using Prolog. And you'll notice a couple of things. Well, the file name extension has changed from PL to Pro, which means, yeah, we're using a different Prolog interpreter that's faster. We'd actually bought one for money by this stage. I think we're using Quintus Prolog. And we're now up to, I think, it didn't have version numbers then, so that one hasn't got any version number on it, but it was 2 years later. And Robert Veerding then joined me, and Robert always sort of works the same way. He always starts off with him, so, do you mind if I modify your program a little bit? And then a few months later, or a few weeks later, none of your program is left. And there's a comment at the start that said Joe wrote the original version, but then there's absolutely no lines of code left, and then Robert's rewritten. And then I'd rewrite what he wrote, and we swapped backwards and forwards like this. And so there, you'll see here, I just highlighted one of the two things. I mean, I'm keeping a log here. Whoops. Oh dear. I'm keeping a log here in... Oh, there we go. That's better. And I noticed there that, I mean, I just highlighted a few things that it took 4 days to rewrite all of Erlang. Right, the entire system took 4 days to rewrite it. And because there's only me doing it, and Robert had joined it. And you'll see from the trace log, kind of, we would change receive to make it return a pair, generate error messages, and go added trace, then change them. And these changes are taking place sort of on a sometimes it's a month or 2 months. And these were in response to Shesh and Erlang, because they were building a prototype with it at the same time. And this machine wasn't big. This was a VAX 11750 with maybe a couple of megabytes of memory. So as I say, this like my little mobile phone, this machine is 20 million or 20 to 100 million times more powerful than the machine that we developed Erlang on. Okay, this was equivalent to Cray 1, which is a supercomputer. And at the time, the Cray 1 had a thing with a little bench, and you could sit on it, and it need about a megawatt of power to power it up. So this is a thing. So this was done on a pretty slow computer, and you see that because of this wasn't blindingly fast. Okay, so you'll see here that reds on run. This is the number of reductions per second that the system was doing. It was doing 245 reductions a second. A reduction a second is a function call per second. Okay, so it's doing 245 per second, and then I optimized it a bit, and it went up to 283. So that's pretty good. This was actually fast enough to build the prototypes of the telephony system, but they were running very slowly. And at that stage, we said, let's make a product out of this. We thought the semantics were okay, but the performance wasn't. And Shesh and they did some work and came to the conclusion that if we could make this thing go 70 times faster, then we were in the right ballpark and we could make a product. So we kind of split into two groups. They were going to make the product, and we were going to speed up Erlang by a factor 70. It actually turned out that 70 wasn't enough, and they really wanted 4 times that. They actually wanted to go 280 times faster, but we didn't know that at the time. So off we went, and we said, okay, let's do this. And let's do all these other things, because we need courses and documentation, and we need a bit of performance. And so we had a little, we set up a committee, and do you remember this program? It was called Blackmail. It was a PostScript program that made this. You just put it in text and then bunged it in and sent it to the printer, and it printed that. Do you remember that? Did you use it? Steve, did you use that? Oh, well, never mind. I thought people with grey hairs, this was old Unix days. It's great. That's a PostScript program that does that. And we developed courses because people wanted to learn Erlang. Because at that time, Erlang wasn't really developed, and you actually had to know quite a bit of Prolog to program it, because the control logic was in Erlang, but when you did computations, it was in Prolog. So you also had to learn Prolog. So made the first Prolog course. Where we go. And here's the slides from the first Prolog course. This is before PowerPoint. I'm not very good at drawing, but I think things like PowerPoint just sort of totally destroy creativity, So we gave all these courses in Prolog and did all our own slides. And that's the only slide that's left from the first course, which I think is rather a shame, because I rather... Sorry? You sell that on eBay. Yeah. Oh, this is the original, Oh, this is my pension fund. Right. And then there's documentation. So, of course, sorry. Yeah, it's a head and a tail. Yeah, this is the head of a list, and that's the tail. And when this is the bar operator chops the list into a head and a tail. Yeah, right. And then there was some, it's a commercial quality product, so you need to write some documentation. And so we wrote the first ever Erlang manual. And so here I can reveal the first ever Erlang manual. I have the original at home, scanned. Do you think I should sell that? I should frame it. So this is the entire documentation for Erlang version 1.05. That is it. That's the total documentation. So, And of course the users, they bitch about documentation and say, well, there's not enough documentation. Right. So what happens now? Okay. Oh, and it had online help, actually, which just printed out that documentation. Performance. So what happened about performance? Well, performance was poor, and this is a kind of, we played a lot. So first of all, this is Erlang. This is the number of Erlang reductions per second against time, and around about 1987, 1988, it's running at 300 reductions per second. And the green and red means the green bit was the experiment bit, and the red bit was the production, when we put them into production. So we ran up to kind of in this domain here, and this ran up to about 1990. We needed to make it go faster, and that was the, didn't really understand how to make it go faster. So the first attempt was to compile it into a programming language called Strand. And Strand was a concurrent logic programming language. And that was when I made a mistake, which I never made again, actually, and that was telling people the result of a performance measurement that will happen when you've written the program without actually writing the program. So we said, well, when we've written the program, it's going to go 20 times faster, we told everybody with great confidence. Although we'd never written the first, I will never, ever make any statement about performance that is not based on measurement. And I will never, ever advise anybody on how to write their code without saying, write it, then measure, please. I just will not speculate. I know it, and I think people who do speculate about this should not speculate about it, and they should write it, run it, and measure. Okay, because it's just counterintuitive. I mean, there's no algebra there. If A takes time t1 and B takes time t2, if you do A followed by B, is it going to take time t1 plus t2? Nobody in the planet has. There's no algebra for that. Nobody's got a clue. It might be faster, it might be slower. Who knows? You know. Right. So there was a kind of gap between here, and we had to figure out how to make it work. And then Robert had collected a whole bundle of papers on how things like the Warren Abstract Machine worked and the Strand virtual machine worked, and he collected all these papers. He hadn't read them, but he collected them all and put them in a file. And I remember I borrowed this file and took it home one weekend, and I read every single paper from beginning to end. And I understood nothing. And it was just a complete, I don't understand anything of this. And then I think on Monday morning I went into work, and suddenly I went, oh! And I understood it. Something happens in your brain, you know, there's this, take information in and try to understand it, you don't understand it, and then go to sleep and things. Your brain rearranges the information you fed. And the thing is, all these different papers, they were all doing the same thing, and I'd misunderstood what it was. Right. And so I then, as a basis of that, built this thing, the Jam, which was Joe's abstract machine. And that is sort of, I'm going to tell you how Erlang works, actually. So the Jam, here's the Jam, and this started here, right? So how does Erlang work? How does it really work? It sort of works the same way even today. So here's how Erlang works. You've got an abstraction. Okay, well, this isn't really abstract. This is how it really works. Every process has got a stack and a heap and a set of registers. Okay, the registers aren't real registers; they're just an area of memory. And the stack and heap have got a couple of pointers into them. You know, everybody knows what stacks and heaps are. Yeah, right. So suppose in Erlang you say x is the tuple rectangle with a couple of integers in 10, 20. So ask yourself, what does that look like in memory? Okay, so it's got to be put into a 32-bit machine containing tagged pointers, and we take about, say, 5 or 6 bits for the tag, and the rest of the word is a pointer. Okay, so a tagged tuple has a tag that says T, I'm a tuple, and it points to the heap. And on the heap contains words containing tagged tuples, and the first one says it's got an arity tag, A. I say, I'm an arity tag, and I say, whoa, I've got 3 things in my tuple, okay? Because a tuple with 3 things in. And the first thing is a rectangle, so it's got an atom tag, and it points into the atom table, okay? And I is an integer, it's a direct integer, so it's 10 and I is a... So that's how it looks in memory. And it's still like that today. Hasn't changed, okay? It's also the reason why there is no atom garbage collection, because everything is sort of interred in this atom table, and you can't really rearrange it in a simple sort of way. Right, so that's the memory layout. So if we have to ask ourselves, okay, so suppose what are the instructions we need to build that thing? So we'll build it up in 3 steps. So we can build that tuple. What instructions do we need to emit to create a tuple with 3 elements in? I say let's just invent a language. This is what it's all about. So here, I'll make 3 instructions: push int 20, push int 10, push atom rectangle, and then it sort of goes up there, and then make tuple 3. And you can understand what each of those instructions does. So the first, here's you have to imagine what it looks like. Push int 20, what does that do? It pushes one of these tagged integers with a 20 onto the stack. And the second instruction, push int 10, that pushes a tagged integer 10 onto the stack. Push atom rectangle, that pushes these onto the stack. Now you've got 3 things on the stack. And the final instruction is make tuple 3. And what does that do? It says, remove the top 3 entries on the stack, put them on the heap, and replace the top entry on the stack with a pointer into the heap. Very simple, right? Any fool can do that. Right. So the compilation of this little bit of, okay, so suppose I'm going to compile that stuff. Then I'll compile, so suppose foo is a function that returns the tuple 10 ABC. Then the compiled code for that is going to look like enter foo 0, enter the function foo with 0 arguments, do this push atom ABC, push int 10, make tuple 2, and return. Really simple. It's about the simplest code you can imagine. If you take those 2 instructions, turn them into a byte-coded machine. Push int means the bytecode 16. 10 is a 10, it's an immediate integer. Make tuple is the bytecode 20. Make tuple 2 is like that. And then you write the C. So it says, it's just a switch statement, and it says switch case 16, push a short int onto the stack. stop++ is baked into PC star ++ break. That's it. It's no more complicated than that. That was the jam. Okay? So, and that, yeah, it works. It's fine. So, the first thing to do then is to write a compiler for that and test that it works. So I wrote the jam compiler. There's even some annotations, sort of, couldn't decide what it stood for. What is going to be called Joseph? Joe's own super Erlang programming house. No, that didn't work. I couldn't expand Joseph into anything. Or could it be called Joe? Joe's own engine? No, it was Jam, actually, Joe's abstract machine. And so did this and wrote this. These are the instructions. They were still in Prolog, because we're still in Prolog. And when we compiled this, I also wrote an interpreter for it to execute these instructions to check out that the machine worked. And then the interpreted code, when you interpreted that code, it ran at 12 ERPs. And then when you compiled it, ran at 35 ERPs. So we're getting there. It's going, the virtual machine is working. But it's slower than the real one. If you remember the previous couple of slides, we're running at 1,000 instructions per second, and this is running at 35. So we're actually getting great stuff, because we're now emulating the instruction set of this. And all we've got to do is write that in C. Okay? 35 ERPs. Right. So I started writing C. Now, I am the world's worst C programmer, because it's so fucking complicated, I can't understand it. And it's got these things called pointers, and I don't have a clue what they are. All I know is that whenever I write C, my pointers always miss by 1 from where they're supposed to go. And I don't know how to use a debugger, because I use printf statements. Anyway, so I wrote this, and then Mike Williams came along and declared my C to be the worst C ever seen on this planet. And so he rewrote this, and that was the. Now the team is up to 3, and we're here. Wait a moment. There. And, whoa! Don't do that. So here we are, 3 people, and that's Mike, Robert, and I, and we kind of split the work up. I wrote the compiler and the virtual machine, sort of designed it. Mike implemented the virtual machine in C, and Robert wrote all the libraries. And here we are, the jam's just coming along here, and then Robert also made the V, which is Vierding's Erlang engine, which was yet another, had a different garbage collector, had a reference counting garbage collector, and it was actually faster than the jam. But when we had to make a decision over what we chose stability over speed and sexiness. You know, there were some things about the V which it was using reference counting garbage collector was rather difficult to get right, and there were certain doubts about how it would behave. Erlang's model was this single stack and heap process, which makes garbage collection very easy because you just garbage collect one process. But the other garbage collectors are a bit more tricky. So we played with all of this and worked quite well, actually. And then came ISS 90. This is all kind of up here. You notice up here, the wars bit, we were totally ignored. There was a big project going on at the same time. And they said, well, just ignore those guys. You know, we weren't doing anything. Then ISS 90 came. It was a big conference, and we had to do some stuff for it. And then in ISS 90 came, oh, there's no sound in this thing. Oh, it doesn't matter. This is the original Erlang movie, which was actually made for ISS 90. Right. No grey hairs as well. Oh, it's a shame without sound, but... Now, this is quite the most Hamish thing in the world, right? So the other thing that's in the history box is, I won't go through all of that, the script. There are 5 phones, pots left, pots right. Something. The audience takes their places, all bells ring. Me see. Do you think we should start the demonstration? I think so. We had script. It's not only it was bad. I wrote the script. No, I mean that's quite funny, I think. And here was a lab at the time. So this is very. This brings back happy memories. I mean, it was great fun in the lab. And you notice, you see the old MD 110 here, which we were programming, and the train set. Now, the reason for this was we were going to show this at a trade fair, and we wanted to demonstrate the idea of concurrency to the guy on the street who could. It's a software idea. So we thought, I know what we'll do. We'll get one program to control both a train set and a telephone exchange. Because then they'll understand concurrency. Well, actually, it wasn't quite true. It didn't really have anything to do with the man in the street understanding. Robert wanted to buy a train set with money from the lab. And this was one of the first Erlang courses, and it was an incredibly popular course. And it had, you could sense where the trains were. Well, you didn't know where they were, but you sensed once they'd gone over the points. And we hold a 3-4 day Erlang programming course. People still remember that course. And the major exercise was, there was one train here pointing that way, and there was another train there pointing that way, and the exercise was to reverse the 2 trains. Right. Now this spurred a lot of development. So the first graphics system was written for X Windows by Jørgen Borger this is McLean Train, and there was a McLean Train graphics programming language, which it could only do one type of graphics, and it was design train layouts for McLean Railways, which was very important for the lab. So why, and also I think at this stage, floating point numbers came into Erlang in order to compute the graphics needed for the trains. So that's why we've got floating point numbers. Right, so 92 to 95, nothing much happened. In this period, I think this is general in periods of software development. I don't really understand why. Some years a lot of stuff happens, and then it goes along and nothing much happens, and then stuff happens, and it's when the stuff happens that it's interesting. We had the first Erlang conferences. Here's the first Erlang conference. Everybody got an Erlang hat, and this this was limited to the number of people who fit in this room, because this was a room we could get for free, and there were 80 people who could fit into the room. And these were all Ericsson people, so there were no external people, I think. No, probably not. And I published the Erlang News, which was, this is early promotional stuff, blindingly fast, Many people think the modern programming language like Prolog and Erlang are slow. Nothing could be further. Sorry? Yes, praise from a convert. After years of struggling with D++, a first-time Erlang user and convert from D++, Peter programmer said, "I just can't believe it," said Peter. What I estimated to take 6 months to write in C++ took only 10 minutes to write in Erlang. Amazing but true. And so we published this stuff, and we had great fun. And we bombed with, there were notice boards it was very funny because the Swedes are very polite and they don't do things. So outside the lunchroom, they built a new notice board to put sort of organizational announcements there. And Bjarne, who was the lab boss, said, we went by every day. Oh, they put a new notice board up there. Went by a couple of days. Nobody had put any notices on it, so I thought, right. And we covered it with Erlang publicity. And then nobody took it down because they're so polite. They thought, until somebody took it down. And then the first of two major events happened. Two events have really dominated the reasons why Erlang sort of came out of Ericsson. And none of these were in our control. The first major event was that on the 8th of December 1995, the AXEN project was cancelled. Now, the AXEN project was a very large project that was taking place in the same building. It had run for 7 years, and at its height had over 1,000 people working on it, and had burnt many thousands of man-years of work. And it was to build, the N stood for new, the new AXEN, the new system of the future. And on the 8th of December, they gave up. And what they'd actually built at that time was some pretty good hardware, which couldn't be controlled by software. It actually crashed. It was written in C++ and used an amazing design system that they'd made. And it crashed after 6 calls went into it, which wasn't very good. Now, we had actually programmed the same hardware in Erlang just for fun, although there was an enormous amount of opposition to prevent us from doing so. And so our stuff was kind of ticking along and doing hundreds of calls and didn't crash. And it was only written by 3 or 4 people. And this was what I call wars, right? So then we got into war. So this is Warlord Wu. Not going to say who he is. But we weren't always friends with everybody in the management in Ericsson. And we were young and inexperienced and didn't realize that calling them complete and utter idiots and things like that didn't go down very well. And also, we weren't very modest in those days. But this is kind of youthful enthusiasm. Programmers, they write some code and they want to show it to everybody and think, oh, it's great fun. And they don't think that, you're a programmer, you've just written what 100 C++ programmers have failed to do. And you want to show it to people because you're quite pleased. And you think they're going to be pleased. Well, they're not. Of course they're not. No. Who wants to be a boss of one sort of pain in the arse Erlang programmer? Or do you want to be boss of sort of 100 C++ programmers? Your salary depends upon the number of people you'll boss over, so you don't want a pain in the arse sort of good guy who speaks this language and nobody else understands. And so we went into war. Let's see. Oh, no, I used to write about. Oh no, forget about that. Well, you're filming it, you see. So then then was a period of following the collapse of the AXEN project. They sort of branded it, and they said, well, let's do it all again. We'll keep all the hardware, and we'll do the software in Erlang. And that was the first golden period, really, because up to that stage, there was no backing from the company to do anything. It was a kind of it was a lab thing. I wouldn't say they were favourable or unfavourable to it, but we didn't have the opportunity to put it into a proper product. Oh, I could say, I hadn't talked about it, the MD100, by the way, was a product by that stage. So it wasn't the case that they were taking an untried technology. That went into a product line called the MD, well, it was the MD110, which was sold, for example, to the European Parliament and still operational today. And it's all programmed in Erlang. And in 1996, this new project started. And a lot of stuff happened very quickly. We were reorganized, and it was great. So it was great fun. And so we get into this period of sort of nothing much happens, but there was a lot of technical stuff. We had resources, we could write proper documentation, do courses, do all this stuff. And that came out to in 1998, 2 years later, the AXD 301 was produced. This is a scalable backbone switch, scales the slowest speed, I think, is 10 gigabits per second or 16 gigabits per second, and it scales from 10 gigabits per second to 160 gigabits per second. It's used by, say, British Telecom in the backbone of British Internet for British Telecom. The only trouble with that is because it will switch up to 160 gigabits per second, about, for a country the size of Sweden, you can only sell one. And, and I think British Telecom bought 3 or something. So I would view it as a great technical success, but it didn't earn any money. Because it was so bloody powerful that nobody, you need to buy one. America might buy 10 or something like that, but I mean, you're only selling a few of them. And actually, the importance of a project has got nothing to do with the difficulty or the beauty of the software. It's got to do with the number of units sold times the profit per unit. Now, if the number of units is sold and the profit is large and the profit per unit is sort of medium, so that product is very high, then the software to do it must be very valuable and very good, and you can put 1,000 programmers on it, right? But if the software, if the number of units times the thing is low, then you can't get any software resources to build it. And it's really like that. You could put 1,000. Ericsson literally has 1,000 programmers working on some of their big products, the ones that earn them a lot of money. Well, I mean, it makes sense. And they'll put a lot of money into the volume products, but not a lot of money into the low-volume products. Well, I suppose all companies are like that. Anyway, so this was a great success. And so then, as a sort of thank you for it being a great success, we were banned. Right. And this is Warlord Wu coming back, because we'd pissed a few people off. And this was the second event that caused us great interest. It was fantastic being banned. Right. Well, not in the way we thought. Okay. And it all turned out very strangely. That's why this slide ends here. Because just before I was banned, I was invited to give a keynote speech at ICFP, the International Conference on Functional Programming, and I prepared this slide, and then we were banned. Right. And so I stopped the slide at the point where we were banned. And I gave this talk about Erlang, and we didn't know what to say, because Erlang was being promoted in the ICFP as the poster child of functional languages. And if I were to go there and say that Ericsson itself didn't believe in it and had pulled the carpet from under its feet, it would have kind of destroyed the credibility of that message, you see. So although we were banned, you see, it wasn't open source, so nobody knew about this, right, apart from us who were really pissed off. And so I gave this talk and things and everything, and I just kind of, the one fact that I just kind of forgot to mention was that it was banned. Right. So banning things has interesting consequences. I talked to a management consultant. He said, banning stuff's always interesting and good, because what happens is like a flower. If you take a flower and you smash your fist into it, then the things kind of splatter out into the ground and they start growing again, and you're losing control now because these things start growing and things start happening. So one of the things that happened as a consequence of that was open source Erlang, because when Erlang was banned, we kind of thought to ourselves, possibly our future is not going to be with Ericsson forever. and it would be sort of advantageous if Erlang was open source. And so we managed through various ways to get Erlang to be open source. I won't go into the details there. But we managed to do that. It took about 5 to 6 months of persuasion and talking to people and arguing and telling them the reasons why it'd be great to be open source. And so, I mean, I haven't really got time to explain all the details. Then, by a very strange coincidence, 4 days after Erlang was banned, all the people who had developed it quit and formed a company. I mean, this is one of these things that it's like a coincidence here. You know, I just happened to be giving a talk here when there's the Erlang conference. And so all the guys who'd done Erlang, apart from Mike, left Ericsson and formed a company called Bluetail. And this was 1998, where venture capital was extremely easy to get. And yes, here we are, 4 days later. And we founded Bluetail, and that was in the days when it's just like the Dilbert cartoons, you know, the spiky-haired technicians and the venture capitalists, and we just went out and they said, "How much money do you want?" And we were totally naive about all this stuff, and I remember meeting a venture capitalist, and he said, like, "You're going to quit Ericsson and form a company?" "Yeah." "How much money do you want?" And we thought, hang on, but we don't know. We hadn't thought about that. No business plan, no sort of calculations or anything. And he just said, how much money do you want? And we thought a bit, said, 5 million kroner. It's about $800,000 or something. And then he said, I can't get it this afternoon. Is tomorrow all right? and we went home after that meeting and had a brandy and so you realise what this means. Yeah, we've all got to quit and start this company. So we started Bluetail, and you know, I said, when Erlang was banned, I couldn't sleep at night, and I thought I was going to get ulcers, and I was worried about it, and all these things happened. But the consequence of that were the open source Erlang and Bluetail. And we sold Bluetail 20 months later for $154 million. So it was kind of okay, you know, because I was one of the owners of Bluetail, and that wouldn't have happened if it hadn't. And then it became chaotic. Notice up to this stage, I have some measure of control, or I wouldn't say control, I have some knowledge of what's going on. I could draw that diagram with all these things, and I knew what was happening. But when it became open source, and when it sort of got out of the door, then these other things started happening, which we didn't know what was going to happen. And one of the big questions we never knew is Erlang going to seed? And we knew if we taught it to people. I've taught hundreds and hundreds of people Erlang. We knew that if I taught them Erlang, or Robert taught them Erlang, that the students understood it. What we didn't know was if people who we had never met could teach it from the books and things, and if it could spread without our influence there. And we discovered to our great amazement that it could, you know, and it began to self-seed, and these things started happening. And so I'm really not going to, because I kind of can't draw these things, I can't really say what happened, so I just got to make jump, so we miss out 10 years. And then sort of 10 years later, and there's all these, suddenly, wait a minute, all this documentation stuff. 10 years later, there's all this stuff. You know, there's books and there's things, and there's all these companies, and they're you know, some of them are pretty big, and Klarna was formed, and then this kind of cool thing happened. If you look back of this, when Gutenberg invented the press, the apprenticeship time was 7 years. You had to work there for 7 years to become an apprentice. And then you were bound to your master for 7 years. And so 7 years later, after a 14-year period, you could start your own printing press. And actually, that's why in the original patents, you were only allowed to patent things for 14 years because it tied into this medieval system. I mean, now we don't have, now it's like 100 million years and it's all done by lawyers. But in the Middle Ages, when technology spread far slower, it was only 14 years. And so what happened with Gutenberg was that the guys who Gutenberg taught to do printing formed their own print shops and spread off and did that. That's what's happened with Erlang, you see, because what we had was the original lab, and it's like the DNA of Erlang. So the DNA of Erlang, it's spread from the lab into Bluetail, okay, and then Bluetail lasted for 2 or 3 years, and it split off, and then its DNA moved into 2 companies in Sweden, TLF and Klarna, and actually, it's quite fun, because if I had to do this diagram again, some guys have quit off from Klarna to form some spin-offs from them and their Erlang companies. So there's some advertising companies under Klarna that already got something like 3% of the world's market in advertising. And in the Stockholm region, there are about 1,000 Erlang programmers. So, I mean, Stockholm's a big sort of lot of Erlang stuff going on there, and a lot of commercial activities. And then there was a side-off split, which is kind of interesting, because Francesco Cesarini, the kind of key figure here, he learned Erlang at the University of Uppsala as a student, and he wanted to do a master's thesis. And he really liked Erlang. So he phoned me up one day and asked if he could come and do a master's thesis, and I could supervise it. And he came along, and I supervised his master's thesis. And then Francesco formed Erlang Solutions after, not immediately. Ericsson had a company called Erlang something or other. Can't remember. Erlang this and that. It was going to sell Erlang and things. And they only actually managed to sell one system. So it was a complete loss. But they hired a lot of guys from the University of Uppsala who were very smart and used them as internal consultants inside Ericsson. And they actually, the hype and the high-performance Erlang and things, that was through this contact with the University of Uppsala. And so they had a whole load of consultants and things that were sort of working inside Ericsson. But then that kind of folded up, and that company never managed to sell anything. Sold one Erlang, one very good. But Francesco formed Erlang Solutions. And then Erlang Solutions kind of grew in this, it's got its own DNA, it's the main consulting place for Erlang. And then I think through Erlang Solutions then started organizing the Erlang conferences, the Erlang factories and all these things. And so this kind of, and holding the course. We didn't want to hold the course anymore. So he starts holding all the courses, organizing all the conferences, and that attracted the interest of Trifork. Now Trifork is a Danish company that was a Java consulting house, but the guy who founded Trifork, Kristin, what's his name? He wanted to sort of move out of Java into some new technologies, and he really believed in Erlang. So he did this JErlang, the Erlang for the JVM, and he's the guy who put generics into Java, and he's a compiler writer. But he founded this consulting company in Denmark. So he became very enthusiastic and came and talked to me about this, and then Trifork, and I think Trifork then bought up part of Erlang Solutions. So we had like 160 consultants here, and maybe 50 or 60 there. And then Basho started, and then so these 3 companies sort of cross-own parts of each other. So we're beginning to build a sort of industrial consortium there on the side. And again, it's this kind of DNA that is spreading around. So that's basically what has happened. That's why I've got all these grey hairs, because it's a kind of, I think in order to, I've had great fun in all this time. I've worked sort of in labs, in Ericsson in the lab, and I've had a startup, and I've been an academic. I got a PhD and done some research and stuff. And it's really nice kind of, that's how I got my grey hairs, it's kind of fun. And I really like to see this whole picture. I don't like sort of academics who just do stuff and the end result is a paper or a PhD or something. Nobody ever uses the bloody stuff. So why bother? And I just don't like all these venture capitalists, what we're going to do, make money, and then what you're going to do, make more money, and then what you're going to make even more money, and so I mean they're fucked as well. So and I don't like. So I kind of like sort of floating around in these worlds and doing stuff. So it's been an extraordinary privilege to take part in all of this and do some stuff. So that's talk number 1, and I've talked for an hour, and I need a beer and a bit of fight to eat. And then when I've done that, I'll give talk number 2. That's a much shorter talk. It's the Sherlock problem, which is a very interesting problem. So, thank you.